So welcome everyone to the February edition of Flower Monthly. It's February 5th, and for all those of you that are watching this later, once we put the recordings live on YouTube. And as usual, we're going to follow the typical agenda for Flower Monthly events. We're going to have a brief welcome message, which is what's happening now. And then I will start with a quite compact but interesting update from the Flower team. And then we'll go straight into our guest talks. So today we are very lucky to have two amazing talks. First, we're going to hear from Massimo. He's going to tell us how he has done some amazing contributions to the FlowerTune LLM leaderboard. And he's going to tell us in particular, I think, about his latest ideas about making the Code Challenge work with a fairly tiny model, which is pretty exciting. We'll hear more about this later. And the second talk would be given by Sina, who's going to tell us about how to build foundational models that are trained distributively for ophthalmic diagnosis, which reminds me a bit to the talk we had in the previous Flower Monthly, which was also about eye images. So first things first, let's start with the Flower update. As usual, I want to remind everyone, because each time we have different type of audiences in Flower Monthly, that the Flower Summit is approaching, and it is approaching very fast. It's going to take place late in March in London. It's going to be a 2-day event, already packed with an amazing series of speakers that you can find in our website, and also a long list of researchers. Many of you are from the Flower community that have built some interesting things with Flower, and you're going to be able to showcase that in either some talks or posters. So in case you haven't registered already, please feel free to do so. You can scan the QR code shown in the website on the slide, or you can just go to flower.dev and click on the link to register. One of the main updates we have from Flower this time around is a new release. If you have been paying close attention, we have been doing one release every 4 weeks, roughly. And this month, well, the previous month of January was no exception. So last week we did the release of Flower 1.15, which is really packed with quite a few exciting features. Many of them happen under the hood, but they are still quite valuable nonetheless. So one of them is automatic node authentication. Previously in Flower, you could establish authentication between superlink and supernodes if you specified the public keys of those supernodes that are allowed to connect to the superlink. That is still an option, but for setups where that's not easy to set up, or maybe it's not convenient because you are doing maybe some prototyping, there is an automatic node authentication mechanism built in. We have also put a great deal of effort in improving the docs, and I will give more details about this in the following slides. There is a new example from the robot, which you probably heard about it in the previous Flower Monthly. It's basically this example allows you to train a collaborative model that learns how to move an object and place it in a particular position. And this is done with the robot framework, which is built by Hugging Face. There is a new baseline called StatAVG. We have also introduced a fairly easy-to-use mechanism to control the log level used by Flower. So for example, if you want to enable the debug logs of all the components like superlink and supernode, now you can do that in a much easier way. And if your client apps or server apps also use a Flower logger, you can also use this mechanism for the same purpose. And we have introduced many other interesting features that makes running Flower apps much easier. One of them is to be able to override some of the federation configs that by default live in the PyProject.toml. Now you can override them from the command line. So this is Flower 1.15, but we didn't stop there, and today we're going to release a small update to 1.15, which is going to be 1.15.1. It comes with 3 main modifications. One is it extends the validity of the logic around the node authentication mechanism that was introduced in 1.15. It fixes an issue that was discovered by some members of our community when you run Flower in Windows machines. And also we updated some of the metadata keys used in gRPC messages. You will be able to update to the latest version very soon, sometime later today. I was mentioning that one of the big updates was the new documentation pages. One of such pages is the Flower Network communication page, which is fairly long and fairly detailed, but what provides you is a high-level view at first of what a typical federation in Flower looks like. You can see some familiar components if you have used the deployment engine, Superlink and Supernodes, the client apps and the server apps, as well as how a user interacts with this system. So through the Flower CLI, like for example, Flower Run, your client app and server app gets bundled, communicated to the Superlink, and then the experiment will start running through the federation. So all these details are provided in this Flower Network communication page. So if you're interested in running things with a deployment engine, this is a great place to start. If you are already familiar with a typical setup, but maybe you have never used a deployment engine, we have also updated the documentation pages that they walk you through step-by-step on how to start from a very simple Flower app that you can create with Flower New, that you could run in simulation. These two pages show you how to run it in the deployment engine. The next one, how to take that and enable secure TLS connections. The next one, how to enable this more sophisticated node authentication feature. So these 3 pages complete the tutorial, let's say. And the last page refers to this mechanism to be able to see a more verbose version of the Flower logs. So I think these are all the updates regarding Flower. You can find more details of all these changes in the relevant posts we put out, either the blog post on our website or the equivalent content in Flower Discuss. So I think without further ado, we can jump straight into the talk of our first guest speaker. Our speaker is going to be Massimo Scamartia. He's a senior DevOps engineer from Onfido, and he's going to tell us about his FlowerTune experience, especially in the coding task challenge. Before I can see, there is a question from the audience which says, will the Flower Summit also be online? And the answer is yes, it's going to be hybrid. Everything that will be presented in the in-person event is going to be streamed through YouTube and maybe other platforms. So for sure, if you are not able to join us in London, you will get pretty much the same experience online. But yeah. Okay, Massimo, whenever you want.
We can get started. Welcome everyone, and thanks for joining. In this session, we are going to explore how a FlowerTune simulation works. And first, an introduction about me. I choose learning AI ML one step at a time as a presentation to myself, as my background, as you see in my description, is of a DevOps engineer. So as a DevOps engineer, our goal is to bridge the gap between development and operations, and we have deal with coding. We often have to deal with containerization. We often have to deal to continuous integration pipelines, deployments, and we have to support the developers. So it's very important for us to understand the infrastructure of the present and also the infrastructure of the future. And as we are also using LLMs, and of course we are using LLMs locally for security reasons, especially when we have to perform syntax correction of code bases, or simply to have help while working. As DevOps engineer, we are working often in operations, so we don't have always the capacity to work on development tasks. And that's the main reason why I was very much interested in the coding challenge in the leaderboard, and also to experiment with small models. So small models that you can run eventually on edge devices, on your laptop, and that are also small in terms of size. So I began experimenting in artificial intelligence and machine learning around 2016, first experimenting with RNNs, LSTM, mostly for text generation. Later, with the early release of GPT models, transformers, I became very interested in the whole open source community and all the development that are bringing us a lot of innovation today, as we see with the recent release from DeepSeek and also the development of small language models that is very interesting. So we can move next about the topics. So why flower? So we are focusing on in improving the research and the development capabilities of small individuals, small organizations, individuals like me that can contribute despite not being fully active in the AI ML research community. So we are going to highlight comparative results between different large language models and smaller models like we have seen with Quen. So then we are going to discuss about the dataset. We are going to explore a bit the dataset that is used for the code challenge and how we chosen this model. What are the reasoning why we have chosen a small model. Then we are going to see an overview about the optimization parameter that we have used during the training process, so for supervised fine-tuning. And then we are providing a breakdown of the infrastructure setups and costs to see how this model has performed also in terms of costs. And then we are going to present the performance results on the benchmarks. So we have MBPP, that is mostly Python challenges, human eval, that is a mixture between different kinds, and we have JavaScript and C++ as a kind of task. So we are going to explore why flower and the core concept of federated learning. So most of the people that are here already know how flower works, so we are not going in depth in this, but we are going just to introduce the concept. So in traditional machine learning, you typically require centralized data collection, where all data is sent to a single location for training. And this approach, unfortunately, can be inefficient, can be costly, and can have a significant risk with privacy. Federated learning works in a different way. So the data is distributed across multiple nodes or devices, and each node trains the model locally on its own private data and sends only the model updates back to the central server. So we can go directly to the second explanation of this, how the simulation engine works, because it's important to say that Flower it's suitable for distributed federated learning, but you can also run a simulation on a single node. And I found that very useful and when experimenting, especially given the possibility that we have right now with small language model that you can run even on consumer devices and GPUs. So we have, as a first step, the Flower datasets that download and partition and preprocess the datasets for the distributed training. And this step is crucial to ensure that each simulated client has its own dataset segmented. Then we have PEFT through the PEFT library for parameter efficient fine-tuning that allows to fine-tune a small subset of the model parameters. This is done for save time and resources. And then you have finally the process of LLM fine-tuning that we are going to simulate a federated fine-tuning setup, and we are going to mimic a real-world distributed training where multiple nodes are going to contribute to the model updates. And finally, the final output is the PEFT adapter. After fine-tuning, we are going to produce this PEFT adapter that can be used for inference and evaluation. So those are basically the components of the Flower simulation engine. And now I'm going to introduce some that I've made for the FlowerTune LLM leaderboard on different domains that I've done in my spare time to explore the framework. So I started at the very beginning with the 7 billion parameter model, the Mistral. I've been continuously interacting with the Flower community on Slack in order to get started, have suggestions. So I'm really thankful to Jan that who has suggested me at the very beginning to try out an instruct model instead of the one that we were trying that was the baseline. This has given improvements in the average. The communication cost still high considering the model size. This had a rank of 3 in the leaderboard. This is in the medical domain that is kind of challenging. There are many different question and answer pair in the data set that can be really challenges. And I've seen that there is also in the first place, a very good contribution that has been also very useful to overlook about some optimization techniques that we are going to see after. I wanted to try it at the same time for doing a comparison about 2 models of the same size. Also the Quen 2.5 7 billion parameters that rank 2. Here I have used different hyperparameters, but mostly roughly the same kind of setup. Probably there is only one small change in the target modules in the layers, but you can find the source code that is available in the FlowerTune main page, the LLM leaderboard. Then I want to try that is not a transformer model. It's a new model that has been introduced a few months ago. That was recalling me my first experience with text generation with RNN LSTM. At the time, this kind of architecture had some limits because it was not leveraging the attention mechanism. With long context, I was not performing well, but it was still promising, and I discovered that it has been released recently on Hugging Face with research by NXAI. So I decided to just to give it a recall to what I was doing 10 years later, just to try out the performance, and was despite the average results are not very high. That's really promising, considering that it's not a transformer model, and I noticed that it's very fast during inference. So the evaluation was quite fast to run compared to the other models. Despite the performance are not really high, that's probably a model that can get more attention in future. Then the Microsoft model, the Phi4, that is a 14 billion parameters model, so a bit bigger. This has been a challenge. A single machine. So I had to choose a bigger GPU with more VRAM in order to achieve this. And here the results are very good. So we were able on the NLP challenge to get 55.64%. And this is ranked at the 2nd position in the challenge. And then finally, the model that we are going to focus today is the Quen 2.5 encoder 500 million parameter instruct. So it's instruction fine-tuned in the code domain. And this has been ranked first, and we can see the communication cost just 8.9, roughly 9 gigabyte. And the average, for considering that is a very small model, the 34% is absolutely really promising. So we can go next about the dataset that we have chosen, and here you can see a link for the code submission where you can see also the baseline. So about the dataset is an instruction dataset where you have the instruction, the input, and the output as a feature. You don't have additional labels that could have been used in distributing the data across different nodes, like a label describing the language, the programming language, or the kind of challenge could have been usable. But anyway, we use this in 20K samples. In this strategy, we are going to use 10 nodes. They are simulating 10 nodes, so the total number of node partitions. So this is 10K that gets 4,000 total number of training samples. That's only 2 clients. That is 10% of the simulated nodes. So the fine-tuning process on only 4,000 of those samples. As by looking at the dataset, I've seen that the question of answer pairs, SOMA, are really challenging, even for human beings. So I decided to choose a model, a small model, but I decided to choose a model that was already instruction fine-tuned on coding tasks. So as I already had experience during inference and fine-tuning with the Quen models, I found very good quality code tasks. So I decided to go with this. Also because it's a small model and it could be very interesting also to trying out converted merged with the base model, converted quantized in the GGUF format, and to try to run it on edge devices or without a GPU for inference. And it has a 32K context length, and you can find more details about how the layers are structured for this kind of model by looking at the Hugging Face page or the research paper. So we are going then to see the hyperparameters that we have chosen to fine-tune this model. And here you can see the link of the Quen 2.5 coder family. So for this setup, we have chosen to use a mixed precision setup. That main goal to improve both the performance of memory efficiency and also the total time of the training. So first, floating point 16 is a format that is designed to reduce memory usage and to increase speed. So it has the same 8-bit exponent as FP32, and that means that it can handle a dynamic range of values, but it uses only 16 bits in total. This allows faster computations. For operation, anyway, for operation like matrix multiplications, we use TF32, float32. That is been introduced by NVIDIA Ampere GPUs. So in this case, if you are using an RTX GPU, this is going to be supported. And it also uses a 8-bit exponent that provides a good balance between precision and performance. And finally, we applied also Flash Attention V2. Flash Attention V2 to optimize the attention mechanism that is helping to provide speed and memory efficiency as well. And for the optimizer that is using during the super process is the choice was paged Adam W 8-bit. That is a memory efficient version of the Adam the W optimizer. So it uses 8 precision as well for certain operations. So we can move next. So yeah, talking about previously, I was mentioning another submission in the medical challenge that has been using this technique. So this DORA, that stands for distributed optimization and rank adaptation. That is a new technique and a new approach that is, in this case, is targeting the specific modules like down project, gate, up project, O project, and QKV project that are key components in the transformer attention layers. So the configuration is including rank that is set to 32 to control the degree of the parameter adjustment, while alpha is set to 64 that scales the optimizer learning dynamics. So those optimization, I found them to be effective because I before trying DORA, I tried with LoRa, and I've seen an improvement in accuracy. So you can see below a link to the paper if you want to learn more about this. Then for the training setup, we chosen a batch size of 8 and 10 steps per round. And how it works that the simulation starts the fine-tuning in rounds in total. You can configure that parameter is possible to be configured, not the number of nodes, but the number, the fraction fit, the number of rounds is something that is valid for the submission that you can change. So in this case, you have a small percentage of the clients that are participating to the round with a fraction fit of 20%. And the strategy is the default one that is the same as the baseline for is fed average that is useful for updates from the client. Then, as said before, we are going over rounds, but with the cousin annealing scheduler, as this is the same as the baseline, as the implementation that as is provided in the examples. So the learning rate, I just made a small change to reduce a little bit the range because before the minimum LR was I think 1E minus 6. I just changed that a little bit. I found some improvement in the accuracy and for the training strategy as before, we used the federated average, and for the step LR is constant, so it's always the same per round for each node. And now we can go to see finally the evaluation results. So I also put a link of the code contribution here. It is the same that you can find in the FlowerTune leaderboard. So for the first task, MBPP, the model performed 25.80. 3781. As you can see, the performance is improved for the JavaScript. That could make it a very good JavaScript Pocket companion, and for the C++ as well. So that's very good results, I think, for a model of this size. And finally, about the costs, how much we have spent for this experiment. So in total, I can tell you that for the experiments has not been very expensive. Of course, there has been a lot of work development, so I spent some time and some money in computing in order to learn all this process. But the process itself, the training process itself, if we are going to exclude the dataset download, the package installation, the provisioning of the instance has been going really, really fast with this kind of model. So I chosen a a GPU that could be comparable to a consumer GPU in terms of memory and VRAM, and maybe also for the architecture, because I think that most of the RTX NVIDIA GPUs are supporting the precision that we have used this. So this could make possible for everyone to start experiment by their own, even with consumer devices. Or as I did by renting a VM, like I did with Kudo Compute, that is offering very good solutions, also leveraging on underutilized compute. The training simulation cost, so we can see here the breakdown with all the components, how much they costed on Kudo Compute. And as I said before, those are the costs on the fine-tuning, without the time taken for the download, without taking in account the network costs for downloading the datasets and the model weights. So this is just compute time for the training, and the model has been trained in 32 minutes and 4 seconds with a total price of 18 cents. So we are close to the end. So the first takeaway is that model size, it really looks like the model size isn't everything, that the Qwen 2.5 coder billion parameter model, despite being small, can surpass much larger 7 billion parameter models with proper fine-tuning. Then, that we achieved this efficiency used mixed precision, quantization, and federated learning. Also, the way the data is distributed, I think that played a role in probably in getting the model generalized better on unseen data. And then I just encourage everyone to join the challenge, to contribute to the FlowerTune LLM leaderboard, to experiment with the Qwen model, with the open source model that you can find, because participating in challenges can really drive innovations, and there are many collaborative opportunities to advance in open source AI that we have right now. Also, to keep it ethical, to keep it safe, it's very important that everyone contributes, not only the researchers in the fields, the users, the developers, everyone who contributes in open source. So we can say 90% smaller than 7 billion parameter models that achieve a comparable accuracy. We reduced the communication cost also about 90%, which is very important, considering that in a real scenario there are going to occur communication costs between nodes and clients. And this is going to be very costly if you are going to go large scale. And keeping that small is very good result. And yeah, of course, that these outcomes demonstrate the potential on how efficient federated learning can be. So thank you very much. If there are some other questions, yeah, I'm here.
Well, thank you, Massimo. I think this was super interesting talk, and I really like the way you break down all the details from all different angles about your submission, like including the costs and the hardware you run. I have one question. How much fine-tuning, and basically how much tweaking of hyperparameters you had to do to come up with this, best entry in the code challenge? Like, did you run, let's say, 10 experiments with different hyperparameters and different settings, or are we talking more about dozens of experiments?
Yeah, it took a while to experiment. So the 7 billion parameter models at the very beginning, I found really hard. And then at some point I thought that maybe it should have been better to start to experiment, and also to do some to add the evaluation during the training. So to use an evaluation data set or the evaluation split in order to, that could have been improvement experiment. The advantage of running a small language model in this case is that is very fast. So if this can run in 30 minutes, then for me It has been only, for instance, okay, run the thing, then trying out, get this higher, get this lower, try to experiment with the rank that was important for the size, for the communication cost as well, to experiment with not exceeding the communication cost that is most important for bigger models, but also for smaller models to keep in track the communication cost. Then I've been reading a lot of open source code, so I was very interested when the small LM2 came out from Hugging Face. I was seeing how they are doing the fine tuning, the optimization parameter that we were using. I think that I taken the page that Adam knew from them. And also for other things, it's all it's all open source interaction. So you basically watch other people work and you try to iterate and to put the things together. And this is something that we do on a daily basis as DevOps engineers when
Yeah.
putting as a generalist put the things together.
Okay, cool. Well, great. Maybe there are some other questions from the audience, or maybe Jan. I think I see Jan Gao is in the call. He's the mastermind of the leaderboard. I don't know if you have some questions for Massimo. Maybe you all have already interacted, so maybe there are no more questions, right? Or maybe William, you have some questions, or anyone else.
Yeah, I just have a general question. Yeah, by the way, thanks for the great talk and also the contribution to the leaderboard. So given your experience on the leaderboards, do you have any like suggestions or tips to other participants?
Well, for the developer experience, maybe adding a more detailed tutorial on how to navigate, because sometimes the difficulty that we have, I'm not talking about Flower, talking in general of dealing with different version, and for some particular model or experiment you need to have CUDA version 12. In another experiment, maybe the way we handle the virtual environments, if we can use PyEnv, we can use I don't know, poetry, UV. These kind of things can be really useful because there is a large interest in IML from Python engineers that could be actively contribute also in improving the developer experience, but also as DevOps, as a experiment and try to deploy these things in VM in a safe way in a VM by following security standards. I think nowadays everyone can contribute. That was the great thing about Flowers, the inclusivity about the community. So I really feel welcomed to give my point of view despite not being in the field. So that's something that Flower already did really well in improving the developer experience. And also thanks Jan, also to you, because you suggested me the Flash attention V2 and many other things that you are being really helpful for this challenge.
Cool, thanks. What would be the next submission in your mind?
Maybe working together on something. Let's see. That could be maybe another small model. Yeah, but I would like to iterate also with the community and give also some space for the people to iterate over the baseline submissions that we have and try also to new models, new techniques, new things, and then keeping everyone in the loop thanks to the Slack channel and the community.
Maybe something for the finance leaderboard would be cool to see.
Yeah. Well, thank you very much, Massimo, for the amazing feedback and the presentation as well. So this was Massimo telling us about how he came up with this top entry to the coding task in the FlowerTune leaderboard. And now we're gonna go to our next guest speaker. His name is Sina Gholami. He's a PhD candidate at the University of North Carolina at Charlotte. He's gonna tell us about a piece of work titled Distributed Training on Foundational Models for Ophthalmic Diagnosis. And I believe in the call is also Professor Minah Nuralam, who is assistant professor at the same university, and I believe you both have been working together. So the floor is yours. Looking forward to hear everything about this.
Hello, everyone. Once again, my name is Sina, and so I'm excited to present our work on distributed training of foundation models for ophthalmic diagnosis. This research is supervised by Professor Minhaj Nualam at University of North Carolina at Charlotte, UNCC. In this presentation, I will walk you through how federated learning can be used to develop robust and scalable AI models for ophthalmic disease diagnosis while ensuring data privacy and generalizability across diverse institutions. So let's dive in. Here's the roadmap for my presentation. We'll start with an introduction, then covering motivation and background of this research. We'll discuss the challenges in ophthalmic AI, introduce our proposed framework that integrates self-supervised learning, domain adaptation, and federated learning. After that, we'll go over our data set, experiment setup, and the performance of our models before concluding with key takeaways. I hope by end of this talk, we'll understand how federated learning can significantly improve real-world AI application, especially in ophthalmology. Well, this work is conducted at Quantitative Imaging and AI Lab at UNCC. Our lab focuses on integrating AI into medical imaging, aiming to enhance disease detection and classification using deep learning techniques. To give you a little bit of background, vision impairment is a major global health issue affecting 2.2 billion people worldwide. And what's more concerning is that nearly 1 billion cases could have been prevented with early diagnosis and treatment. Among these leading causes of vision impairment are diabetic retinopathy, age-related macular degeneration, and glaucoma. And we can see some of the example of patients with these diseases. And these diseases can be detected through imaging techniques like optical coherence tomography, or OCT for short. However, early symptoms are often difficult to identify, leading to late stages of diagnosis when treatment are less effective. So how can AI help? Let's take a look. Well, to understand how AI can improve diagnosis, let's first look at retinal imaging. There are different imaging modalities used for ophthalmic disease detection, and two most common ones are fundoscopy, which provides a 2D images of the retina, and then there is OCT, which captures high resolution cross-sectional images of the retina, enabling detailed structure analysis. And probably you have experienced sitting behind of this desk to check your retina. And OCT is especially powerful because it allows clinicians to detect subtle changes in retinal layers, making it ideal for diagnosing disease like diabetic retinopathy, DR, and age-related macular degeneration, or AMD. These are some of the samples that we've taken in our lab, comprised of OCT that captures the structure, and also OCTA, OCT angiography that visualizes vascular flow, helping detect early signs of retinal disease by highlighting blood vessels abnormalities. So the images, these images on the right side are, are OCTA. Well, while AI holds promise for ophthalmic diagnosis, several key challenges must be addressed here. The first one is annotation bottleneck. Labeling medical images requires clinicians and making annotation very difficult and expensive. Also, different hospitals use different imaging devices and protocols, leading to inconsistencies in data that could lead to domain shift when we train AI models. And of course, sharing patient data across institutions is restricted due to privacy regulations. And finally, many clinical sites lack access to powerful GPU clusters that are required for training large AI models. And these challenges make it difficult to develop scalable and powerful AI model. And to overcome this challenge, we leverage self-supervised learning, SSL, domain adaptation, and federated learning. So let's explore these approaches. The first one is self-supervised learning. Instead of relying on labeled data, self-supervised learning allows AI models to learn from unlabeled images by recognizing patterns and structures. This is especially useful in medical imaging where annotations are scarce. In this study, we used mask image modeling, a technique where the model learns to predict mask patches in an image. This helps the model understand the underlying structure of OCT scans without needing manual labels. And here we see an example of model predicting the mask patches. So SSL helps create more robust and generalizable model. The second technique that we've used was domain adaptation. A major issue in AI model is the domain shift, as I mentioned, and that is caused by imaging protocols, demographics, and devices. This means a model trained on one data set might fail on another. So to solve this, we use this domain adaptation technique, or SVDNA algorithm, that transform images from different sources to the target image, making them more consistent across institutions. As you can see in the images on top, or source images. After applying domain adaptation, the pixel intensity and texture of different scans become more uniform, allowing the AI model to perform better across datasets. And the idea behind this is using singular value decomposition of the target. So we come to the federated learning. It's a game changer for AI in healthcare because instead of sharing patients' data, hospitals train model locally and only sends model updates to a central server. And this method ensures data privacy, that is a major concern in this domain, while allowing collaboration across institutions. It also enhances model generalization by learning from multi-institutional data. And Flower, as a well-known framework for federated learning, is very efficient in managing communication between multiple training nodes and aggregates updates using customizable strategy. And the benefit of using federated learning is that it allows to optimize the resources that are required for training a robust AI model. So it allows to developing real-world applications that are scalable. As we know, federated learning is gaining traction in the field of ophthalmology as several research groups are exploring its potentials. Here, I'd like to highlight some key contributions in the domain. The FedEye platform demonstrates a scalable and flexible end-to-end federated learning solutions for ophthalmology, emphasizing its applicability across various institutions. Another study, researchers focuses on microvasculature segmentation, and diabetic retinopathy classification using OCTA data, showcasing, again, federated learning strengths in tackling specialized imaging tasks. Another study, multi-center collaboration in ophthalmology, highlights how federated learning can be used to enhance diagnosis and disease epidemiology by pooling expertise and data from diverse institutions. And finally, a review of federated learning for ocular imaging provides insights into the progress and future potentials in improving diagnosis workflow. Of course, our lab is one of the leading groups contributing to this space with a focus on federated learning application using OCT data. By building on this growing body of work, we aim to push the boundaries of what federated learning can achieve in ophthalmic diagnosis. Now, let's dive into the detail of our work, see how we contribute to this exciting field. So our goal was to develop a foundation model that can learn robust OCT representation using SSL, handle domain shift with domain adaptation, and train collaboratively across hospitals using Federated. Of course, the model should be able to classify multiple ophthalmic disease classification with high accuracy. And we would like to ensure scalable, privacy-preserving AI for ophthalmology. So let's break down the stack, our framework. The first one was, mainly we had 4 phases. The first one was local learning, where we train a model on a single data set. This approach, of course, lacks generalization because when it was tested on external data, the model performed poorly. Then in the second approach, we conduct a centralized learning, where we combine all the data into one machine, apply self-supervised learning with mask image modeling for pre-training on all the data, and then fine-tuning over each data set. It has good performance, but there was a privacy concern. The third one was federated learning. We pre-train a global model across different data sets without sharing data using MIM and federated learning. And then each node fine-tune the model, the federated learning model, over its own data. And eventually, the most advanced method that we use, we integrated the domain adaptation into the previous phase to improve generalization. So for local learning and for fine-tuning, we followed the conventional deep learning pipeline, consists of image transformation, an encoder, a classification head for predicting the input level. And for self-supervised learning, we have implemented mask image modeling with 50% masking rate in the center of image, ignoring the top 20% and 20% bottom, as they are usually black pixels in OCT images. For the federated learning, we use Flower to orchestrate the process. Each node pre-trains locally and sends the model updates to the central server that resides at UNCC, and then the server aggregates these updates using FedAverage. We pre-train models for 1 to 5 rounds and compare the performance. Then for the domain adaptation, we put a target image inside the server. The server aggregates the eigenvalues and eigenvectors of that image and sends it to each federated learning nodes via fitconfig method. Then each node ran on fly the domain adaptation transformation to apply this transformation on their own data. For our purpose, we use 7 OCT datasets, including 6 public and 1 private clinical data from UIC. And for federated learning, so we simulated 7 nodes. Here we can see different percentage of data allocated to each phase for training, validation, and testing. Consider that the DS7, the major part of that was considered only for evaluation. Each data set has its own unique set of labels. So we considered a multi-class classification problem for each of them. You have 7 different problems. There are also common labels between these data sets. So we use that common labels for external testing. The model that has been trained on DS1, then tested on other data sets. And again, to clarify, for each phase, for example, for local, centralized, federated learning, and domain adaptive federated learning, we trained 7 different models and then evaluated them on internal and external test sets, except for DS7, which was a unique external data sets coming from UIC. And we tested different hyperparameters, image resolution, and optimizer to come up with the best numbers. And for federated learning, once again, we have 7 nodes, 6 of them with the server at UNCC, sorry, and 1 of them at UIC. So to compare the performance of our model, we use macro AUC-ROC for multi-class classification problem. As you can see, the SSL-based model outperformed local models by 10 to 40% across different data sets. And FDL5, that is federated learning, that means federated learning model trained for 5 rounds. And that FDL is domain adaptive federated learning. They are also achieved good performance. When we tested on external data sets, we can see that that FDL5 achieved the highest generalization performance, that demonstrating the value of federated learning and domain adaptation. And when we check the performance on DS7, we can see as we plotted the AUC-ROC for different approach, local, central, domain adaptive federated learning, you can see again that FDL5 achieved the highest performance. So in conclusion, we implemented a framework that has privacy preserving, no raw data ever leaves the node. Federated learning ensures that patients' privacy is fully maintained, addressing concerns around data sharing regulation. This approach was scalable because we can easily accommodate a new node without requiring them to share data. It reduced the need for annotation. By leveraging SSL, we can minimize the number of labeled data. And of course, this framework is robust because it can learn from diverse imaging conditions and devices. These benefits makes this our framework highly for real-world medical AI applications, especially in ophthalmology. And thank you all for your attention. And if you have any questions, I'm here to answer. And I would like to thank our collaborator.
Great. This was a fantastic talk, Sina. Thank you very much for providing all the details. And I think also it was amazing to see that there are some live captions for your talk. That was quite, I've never seen it before, so that was great to see for the first time. I have one question, in particular, when you were talking about domain adaptation, you were saying some of the sources of these domain adaptation issues would be maybe different sites, different hospitals using different protocols, maybe different devices, populations might be different in different hospitals because of how demographics are distributed.
Yeah.
Were you able to identify which of these is the most problematic one? Or do you have some theories of which one is the most problematic in your particular study?
In this study, we found out the device itself makes the most contribution to this domain shift. As you can see, these are different images, random images, taken from different data sets. These are like 7 images coming from these 7 data sets. And each of them has taken using different device. And you can see they have different image intensity. So we randomly pick some subject, one subject, and we put it here. And you can see the device that they used is basically affects the most on the image intensity. And there are like different devices on market, the different OCT devices on market.
Okay, interesting. So I know that your method was built to overcome these shifts, domain shifts, but even before, for example, instead of leaving all that task, potentially very difficult task to the model and the learning stage, did you consider doing some data homogenization to homogenize all the, or pre-process all the data sets in a similar way each side? Or do you think some of these, I think these things are not easy, especially in FL when you don't have access to the different sites, right? But I think there are some level of pre-processing that could be executed in every site. Do you have some thoughts about that?
I would say in federated learning, especially in this medical domain, where you have restricted access to their data, you probably rather sending all this configuration from the server to each node. So in our implementation, we put the same image transformation for SSL, and for fine-tuning, again, same image transformation. For example, all the images would be resized, all of them would be normalized. But also apart that, we've seen adding this domain adaptation can improve the performance of our model. So we said, okay, apart from this, we can also apply domain adaptation, and the configuration, once again, can be sent from the server to each of these nodes.
Okay, yeah. That's one way to
Hi, Javier. I just had a quick comment on that. By the way, really nice talks, and thanks everyone. One of the things that we wanted to do is like one of the beauty of federated learning is we are able to use data from different sources. So ideally, we would want some difference in them because they're coming from different demographic profiles, right? So the scope of domain adaptation is not just homogenize them, is just keep their uniqueness, is just if there is if we can improve the intensity, brightness, like those more high level things to make our model more optimized. That's what our goal is. We don't want to effectively change them too much. So there's like a sweet spot where you want them to be different enough, but then so you just don't want to mess with the model convergence. So this is the domain basically helps with that, and that's the goal, I guess. And we also do it randomly so that not say, let's say we do it for dataset 1 as the target image, then we switch it up so that every time it's a little bit different so that the model are not biased. Otherwise, we saw that the model can be biased towards the dataset that has the highest amount of data. We also don't want that because ideally, when we scale this up, we'd have like say 100 institutions, right? And we want the smaller institutions to be taken seriously as well, not just say one institution is like 1 million image data points. So yeah, so we're still working on this, and like this is still an interesting research topic.
Yeah. No, thank you for jumping in with a clarification about, it's not right to try to erase the particularities of each site. I 100% agree. So I think your comment was on point.
Yeah.
Thanks for that. So I don't know if there are other questions, maybe from the audience. I will check on on Slack briefly. If there is anyone with a question, please jump in. If not, I have one extra question. Oh yeah.
I'll just go. In terms of next steps, I mean, I really like the presentation. Is it to add more, organizations to your federated setup, or what's the plan from your side?
Of course, yeah, we would like to include more data from other institutions, from other demographics to our framework, and of course, exploring other federated learning strategies. For example, in this study, we only go for Fed average, but we know that there are many other strategies for averaging that we can also apply here, and we can improve the performance of our global model.
Do you see a need for personalization when it comes to this?
I don't think so, because we pre-train, we are in the pre-training phase was conducted using Federated, and then each of them was fine-tuned on its own local data. So the personalization was somehow conducted, somehow integrated inside this framework. We can, of course, there are other ideas that what if we somehow reduce the number of remove the fine-tuning phase and go from training to inference instead of having pre-training, fine-tuning, and inference. There are some ideas here that we would like to also explore them. But at this time and at this with this framework, there is no need for that.
Great. Yeah, I think that was a bit the angle that William was asking about personalization, whether like the global model you are then doing a fine-tuning in each different site, because in the end each hospital might have its own demographics, like maybe it's a children's only hospital, these kind of things. Pretty interesting. Yeah, I think I was going to ask also about personalization, but I think we have already ticked that box. So I will ask very briefly, and my final question is about what, among all the possible, let's say, dimensions for heterogeneity in each site, we are talking about the domain adaptation related heterogeneity, but there is also like the quantity level heterogeneity, like some sites having much more data than others, because at the end of the day, some hospitals are much bigger than smaller clinics and they have more data. Did you have a chance to explore this aspect as well?
I mean, in domain adaptation, yeah, here there's the slide. Of course, there's the amount of target image intensity that you would like to consider for your source image. You can consider there's like a threshold on how many eigenvalues you want to take from the target image. Because if we go through the algorithm says we remove the least important diagonal values of SVD from this source image and replace it with the target image. That is basically the noise information of the target image. But you can change this threshold to see how much do you like your images to adapt to the target image. And as Dr. Allen mentioned, we do not want to convert them completely to the target image, because that might in this case we might lose some information from these differences. And of course, some devices, OCT devices, are very similar. For example, these 2D images, as you can see in a source image, the first two on the left side. I'm not sure if you can see my
We can see it, yes, we can.
These two are very similar because they kind of use the same device. And then the third image and last image, they also have similar intensity because again, they kind of use the same device. This is also something that we were able to explore, that's seeing what kind of device they have used during the image capture.
Okay, cool. Really, really interesting work. So thank you very much, Sina, for all the details. And if anyone in the audience is still interested in reaching out to Sina, well, Flower Slack is a great place to start those interactions and maybe even collaborations. So I'll share now my screen to wrap up to this February's Flower Monthly. Before showing the final slide, I want to say that after every Flower Monthly, maybe a couple of weeks later, all this content is going to go on YouTube. So you can go through the talks again and maybe think about them a bit more, or pause and replay it again. And I want to highlight the 2 fantastic talks we had in the previous Flower Monthly. One from Eden, and she also talked about her amazing work on medical eye problems and how she solved them with federated learning. And the other talk was by Evelyn, where he presented the very first federation of robotics that collaboratively train an object manipulation model. So these are live on YouTube. You have the link down there. And these are only 2 videos out of many other amazing materials we have in our YouTube channel. So do not hesitate to take a look. And with all that said, this is the end of February's Flower Monthly. The next one will be on the first Wednesday of the next month. That's March the 5th at the same time, 4 p.m. UTC time. So I hope to see you all there. And thank you very much once again to our speakers, Sina and Massimo. And thank you all for being here with us. Take care.